In this lesson, we're talking about discrete random variables, which are random variables that have probability 1 on a discrete set D. I've listed a couple bullets here to sort of describe to you quickly what a discrete set is. It's either a finite set or a countably infinite set which does not have limit points. And if you want a more formal lesson on this, you can follow the link here to the calculus section. But it involves topology on the real numbers, so it's probably a little more advanced than you need, well, for certain for the actuary exam and probably for an undergraduate probability course, if that's what you're taking. So you don't normally need to know how to formally define a discrete set. But you could think of it as opposed to a continuum. So a discrete random variable is going to have a value like 1, 2, or 3, whereas something like the amount of rainfall that falls could have a value like 1.27365 and so on inches. And as you get more and more accurate measurements, you can measure it out to more decimal places. That's not a discrete random variable, typically. A discrete random variable would have an outcome like 1, and it doesn't matter how close you measure that, it's just 1. So let's take an example. Suppose we flip a coin 3 times, and the sample space of that would be just the outcome of the 3 flips, right? So you could get heads 3 times in a row. You might get a heads followed by 2 tails, which would be that one. You might get a tails, then a heads, then a tails, and so on. And the probability, if we have a fair coin, is just 1/8 for every outcome, right? So all the outcomes are equally likely. And if we let x be the number of heads flipped, then x is going to be a discrete random variable because it's going to take on a value like 0, 1, 2, or 3. So for example, x of tails, tails, heads is 1, and you can't measure that more accurately, and you can't get really close to 1. It's just 1, right? And x of heads, heads, heads is 3. So this would be an example of a discrete random variable. They can be infinite. So for another example, suppose we're flipping a coin over and over until a tails comes up, and let x represent the number of heads that you flip. Well, you could get 0 heads because you might flip a tails on the first flip, which would be 0. But you could also get 99 heads before you flip a tails if you're really lucky, or unlucky, however you're wanting to look at it. But you could keep flipping heads over and over and over again, and maybe it takes you 500 heads, and then finally a tails comes up. So there's not necessarily an upper bound, even though the numbers get less and less likely. So we could let A be the event that x is even, and compute something like that with an infinite series. So the probability of A, where A is the event that x is an even number, is the sum from I equals 0 to infinity of the probability that x is 2i. So if you think about 2i, so I is 0, 1, 2, 3, and so on. Then 2i is 0, 2, 4, 6, and so on. So it's all the even numbers. So we're looking at the probability that x is even, or 2 times I for some number I. And each time we flip the coin, the probability that we get a tails is 1/2. So for the first flip, it's 1/2. For the second flip, it's 1/4. For the third flip, it's 1/8, and so on. So this equals 1 over 2 to the 1. This equals 1 over 2 to the 2. This equals 1 over 2 to the 3, and so on. So it's 1 over 2 to the I plus 1, where in this case, this would be like I equals 0. Right, so there's a 1/2 chance we get 0 heads because we just flip the tails. This is I equals 1, so this would represent we get 1 heads and then a tails. So there's just 1 heads. This would be I equals 2, it would be 2 heads and then a tails. There's a 1/8 chance. So to get I heads, it's 1 over 2 to the 2i plus 1. And we can factor out 1/2, and this becomes just through algebra 1/2 times the sum from I equals 0 to infinity of 1 over 4 to the I, which is by a geometric series 1 over 1 minus 1/4, which is 1/2 times 4/3 or 2/3. So there's a 2/3 chance that x is even. It's not a 1/2 chance because you're really likely to get tails right on the first flip. So there's a 1/2 chance right off the bat you're going to get 0 heads. But if you don't get 0 heads, then there's some chance you're going to get 2 heads, or 4 heads, or so on. So it's more likely that you're going to get an even number than an odd number, and in fact it's 2/3. So if you need a reminder on how to evaluate sums like this, follow this link. But you'll often see this with discrete random variables. So in discrete random variables, you're going to have infinite sums. So let's look at another example. A bet is made in which the bettor may win or lose money. Let x be the amount of money that the bettor wins, where a negative amount represents a loss of money. So the probability that x equals $2.50 is 1/2. The probability that x is minus $1.15 is 25 or 0.25. The probability that x is negative 3.14 is 0.25. So I wanted to include this example to point out that discrete doesn't mean whole numbers necessarily. So this is still a discrete random variable because it's one of 3 values. It's either 2.5, negative 1.15, or negative 3.41. But it's not anything on a continuum. So again, you can't measure this more accurately. You're not going to be 2.501176 something something dollars, right? It's $2.50. So it's discrete. So what's the probability that the bettor loses money? You can compute that as the probability x is less than 0, which is the probability x equals negative 1.15 plus x is negative 3.141, which is 1/2. So that's another example of doing a computation with a discrete random variable. Discrete random variables have what's called a probability mass function. And it's represented by a little p, as opposed to the capital P, which represents a probability. And little p of x is just the probability that x, the random variable, is equal to little x. So if we do an example of this, if a coin is flipped 2 times and x is the number of heads, then the probability x is 0 is 1/4, the probability x is 1 is 1/2, and the probability x equals 2 is 1/4. But we can represent this as a PMF with just writing little p of 0. So we don't need to write out big P of capital X equals 0. We could just write p of 0. So these two represent the same thing. And this is just saying the probability that x equals 0 is 1/4. And then here's the probability that x equals 1 is 1/2. So we can even talk about the distribution of a random variable in terms of its PMF without having to write the probability x equals something and something. Since a PMF is representing the distribution of a random variable, it has to satisfy a couple of properties. So for one, the PMF is always between 0 and 1 because it's a probability, right? So p of x equals the probability that x equals x, and the probability is always between 0 and 1. And also, if we sum over all the points in which x has a positive probability, we have to get 1. So the probability that x is a real number, since it's a random variable, it maps to the real numbers, has to be 1. And so this sum also has to be 1. So I guess I included an example here. If we just defined like p of 0 equals 0.1 and p of 1 equals 0.2 and p of x is 0 otherwise, we don't get a PMF because the total probability would just be 0.3, which doesn't make sense, right? So this does not equal 1. So it's not a PMF. However, if we said p of 100 is 1/2, p of negative 2 is 0.3, and p of 0 is 0.2, and p of x is 0 for all of their x's, this is a PMF, right? Because p of 100 plus p of negative 2 plus p of 0, all the points on which we have a positive probability do sum to 1. So this is a PMF.